In this video, I'm going to cover the law of sines. It is the first of two topics that show us trigonometry can be applied to non-right triangles. That means that we can figure out angles or sides without relying directly on the trig ratios that compare the opposite, adjacent, and the hypotenuse. If it has not been mentioned before, in any triangle, we label the vertices with capital letters and the opposite sides with the respective lowercase letters. So the picture that I have here, which is not a right triangle, has vertices A, B, and C. Okay, so what we're going to do is designate the names for the side links across from those as the lowercase of these letters. Okay, so across the figure over here, this is going to be lowercase a. Across from B is going to be lowercase b, and across from C is going to be lowercase c, which is a little bit harder to identify because it looks exactly like capital C, but just smaller. All right, so here's what the law of sine says, which is a really simple and almost convenient thing that we could get. It says that if we were to take the sine of any angle in the triangle, okay, take the sine of any angle that's here. So if we took the sine of A, whatever that angle measurement is, and you divide it by the side that is across from it, that quotient is going to be identical to taking the sine of another angle like B and dividing it by the side that's across from that one. Okay, so you see it's three-part equation here because it says that it doesn't really matter which ones we're looking at as long as that they are opposites of each other. So if you use the sine of A, capital A that is, and divided by the side across from it, it's the same thing as the quotient that you would get for using the B's, which is the same thing as you would get for taking the quotient of sine C over little c. Okay, very convenient thing here. Now, you won't ever actually solve a problem that looks like a three-part equation like this. You'll only be using two at a time, which means that it would look like a proportion, which also means that when you solve these, you're just going to be using cross products. That's generally all you need to do here. In some cases, there's one extra step that goes with it, but overall it's cross products, which is one of the basic types of solving in mathematics that you had learned probably around sixth grade, so well before you even got into high school. So what we're going to begin with is a proof here. We're going to prove that the law of sines is actually true. Okay, we're going to do that before we actually start doing any of the problems. Okay, now remember that trigonometry is based in right triangles. So all the stuff that we did before with the ratios, like the sine of an angle is equal to the opposite of the hypotenuse, all that stuff is going to come into play here, and it's going to actually prove that you can do this. You can do the law of sines with any type of a triangle you have. Oh, as a side note, you can actually do the law of sines with right triangles. There's no restriction to that. There isn't a restriction to that, and you can start applying what you see here in those older problems if you want as well. All right, so the beginning place for all this is to actually make right triangles. Okay, I'm going to draw a perpendicular from point C down to the base here. So I'm going to force that to be perpendicular. And when I do that, I end up creating two right triangles. Okay, I'm going to take a look at both of them, but I'm going to start with just what we have here to the left. All right, I'm also, when I draw that segment, I'm going to go ahead and introduce a variable here. The really neat thing about this variable is that I'm going to use it for just a short bit, and then it's going to remove itself from everything. So it doesn't end up being anything important in the final part of this stuff. It's just it's a neat little filler for a moment. Okay, so now that I have that there, what I can do is start creating some trig ratios that we're used to from the beginning. Now, I don't have a description for this side right here, but I went ahead and added in an x there. And I do have the hypotenuse described as little b here. Okay, so if I think about these things, this is the hypotenuse with respect to A is what I'm looking at here. With respect to A, the hypotenuse is little b, and then we also have the opposite side, which I'm calling x. So if you think about those two together, the opposite and the hypotenuse, that would be sine. Hence, we're going to be looking at the law of sines here. So I can write this statement. I can say that the sine of capital A is equal to x over b. Okay, the sine of A is equal to the opposite side divided by the hypotenuse. All right, now I'm going to table that for just a moment. I'm going to go and look at the right side, and we have a similar situation over here as well, that angle B, if I start thinking about angle B, then x is opposite to that, and A is the hypotenuse. So I can write another equation that says that the sine of capital B is going to be equal to x over little a. Okay, so I've got these two similar equations. And now what I'm going to do is I'm going to solve both of those equations for x. I'm going to isolate that new variable. And to do that, all you need to do is multiply both sides by whatever your denominator is. So if I multiply both sides here by b, it's going to cancel on the right, and then it'll just show up on the left. Okay, so I get little b times the sine of a is equal to x. Likewise, over here, I'll multiply by little a, so I get little a times the sine of b is equal to x. Now that I've done that, I can actually use what is called the transitive property. Okay, I've got two expressions that are both equivalent to x, which means that these two expressions must be equivalent to each other. So I can take little b times sine capital A and set that equal to a sine b. And as I mentioned before, we use x just temporarily, and it actually removes itself at some point. It was just a filler here so that we could use the transitive property and set these two things equal to each other. Okay, now we got one more step here, which is more about just organizing things, make stuff look a little bit better, because you're gonna notice you got a little b and a capital A together, you have a little a and a capital B together. If we divide both sides by little a, little b, just go ahead and divide both sides by two things at once. Okay, instead of separating this in two steps, I'll just do it at one time. If we divide both sides by little a and little b, these little b's are going to cancel, and these little a's are going to cancel out. And we end up with, if I clean everything up here, you're going to have a sine a in the numerator, but you still have a little a on the bottom. And over here, we're going to have sine b over little b. And that is the law of sines. Now, I don't have the third part attached to it, but the letters are arbitrary anyway, where they were placed, okay? They could have been the different letters. I could use B's and C's where I had A's and B's, and I could have got that. Or I could draw the perpendicular here. If I draw the perpendicular in that position and then turn it, we would see the comparison with B and C. So we only need to do one case, but it does extend to all three pairs of sides and angles. When using the law of sines to solve a problem, there's one of two things that you could be looking for. You could either be looking for an angle measurement, or you can be looking for a side length. Okay, in example number one, what we're going to be doing is looking for an angle measurement. We're going to be trying to figure out what angle T is. Okay, so we're told that there's a triangle RST. Angle S is going to be 126 degrees. Little s, so that's going to be the side length across from this angle, is going to be 12, and then little t is going to be a side length as well, which is going to be 7. Okay, so when I drew my picture, and I haven't drawn the whole thing here yet, what I wanted to do was at least make sure that I had an angle that was obtuse. Okay, because we are told that there's one that's 126. Okay, so your goal here is not to make the pictures look exactly as they're being described, but if you can give them a little bit of the characteristics that are described there, then that's always a little bit better, because you start to believe the answers that you calculate. Now, I just sketched that real quickly, and I haven't even measured it to see what it was, but yeah, this isn't even really close to 126. 126 degrees would have been out here. I'm more around about 105, maybe 104 degrees on there. But the idea was that I made it at least an obtuse angle so that it's starting to get close to how it should look. All right, and then as far as the side lengths here, one of these is going to be allowed to be the 7. One of them can be the 7. The other one, we're not going to know. Okay, let's take a look at why. This is angle S. We have angle S here because that's the 126. So the other two vertices are going to be the R and the T. okay? And we don't know side length r, so it's not like we have an included angle here. Okay, so we really don't know what that size is. So I'm gonna just go ahead and let these be as there are. There's no real reason to start attempting to adjust these for size. I'm gonna go ahead and just let them be, not stress that point. Okay, so across from the 126 is where little s is gonna be. So that's gonna be a 12 across from t. So it really didn't matter which one of these was r and t. We just wanted to complete a triangle. So across from t, that's going to be the 7. So we don't know that side. We also don't know either of those two angles. And what we're trying to find is this angle here. We want to figure out what angle T is. All right, so law of sines is, it's a proportion, ultimately. You just got to set up a proportion, do some cross products. Okay, so I'm going to go ahead and start an outline here. We got two fractions that are set equal to each other. And on the top, you're going to do the sine of an angle. On the bottom, you're going to put the side length that would be across from it. So we do have 126, so I'm going to go with the sine of 126. That is going to be over 12. Okay, and then my other fraction, the goal here is to figure out what angle T is. So I'm going to have the sine of T, that's going to be divided by 7. Okay, so now as we take a look at the proportion that's built, you're going to notice that there's only one variable in here, which is the angle measurement. The thing that you have to see in the law of sines is a complete side to the proportion. That means that you have to have an angle and a side that are across from each other. You have to have a pair like the 126 degrees and the 12. If you don't actually have a complete pair, you're not going to be able to complete one of the sides, which means that you'll have variables on both ends of it and you can't actually use the law of sines. So be looking for that whenever you're attempting to do a law of sines problem. Look to see if you do have a pair. Let that be your first proportion and then you see what you can do with the rest. Okay, once we're here, this is a cross products problem. What we're going to do is multiply these two, and then we're going to divide it by the, I always call it a corner here. You're going to multiply that diagonal and then divide it by the corner that you know. Okay, so let's get our calculators ready. All right, so to multiply these, the way that I do it in the calculators, I just type the regular number. So I just type the 7, and then I'll follow it up with the sine of 126. Okay, so that product is going to be 5.66, so on. Okay, now that number doesn't mean anything with respect to the picture. It's just a kind of middle step that we have here. What we're going to do next is divide it by the 12. Okay, and that answer isn't going to make a lot of sense either. You're going to get back some decimal number. You're going to get back a decimal that's between 0 and 1. Okay, it's always going to be a decimal once you get to that step. But what that represents is this corner. That represents the sine of T. So it doesn't represent the angle measurement T, which we want, because that answer should be somewhere around, we're just going to guess like 40 degrees or 30 degrees or 50 degrees. It should be something like that. It shouldn't be a decimal number. So we have one more step, which is to undo the sine part. Okay. So for that, we're going to press second on this calculator. I press second sine. I want to pull up the inverse sine or the arc sine. And what I want to do is place that answer inside of it. So on my calculator, if I press second negative, it's going to recall the last answer that I had in there, so I don't have to go and highlight it or don't have to type it in. So I can just press second negative. Okay, do that, and it pulls that answer automatically into it. Go ahead and press enter, and I get 28 point, let's just call it 28.2. All right, so angle T, let's do a different color here. Angle T is going to be equal to 28.2 degrees. All right, so now the neat thing is now that you have that angle, which is the end of the problem, by the way, that's it, we're done. But now that you do have that angle, if you've got the 126 and you've also got the 28.2, right, you've got two of the angles, you can technically figure out what a third angle is. Once you have that angle, you could do another law of sines problems to figure out what the side is across from it. Okay, so at the beginning, you're going to start with 3 pieces of information, and that's the same thing that we saw with the right triangle trigonometry. So here you got 2 sides and you got an angle. You did have an angle across from one of the sides, so that allows you to set up the law of sines. But as soon as you do your first law of sines problem, you're going to get a 4th piece of information, which would allow you to find everything that you need to completely solve the triangle. In example number 2, we're going to look at the other type of solving problem, which is solving for a side length. Okay, so it says that a civil engineer wants to determine the distances from points A and B, these 2 points, to an inaccessible point C. So you're going to see that point C is out here in the water. Okay, so the engineer isn't going to actually go out to the water, but he wants to figure out how far point A is from C and how far B is from that point. The engineer does know that AB, that's the distance from A to B, is going to be 25 meters, and he knows that angle A is 110 degrees and angle B is 20 degrees. Okay, so these are all things that the engineer can do from where he's at. So where he's on the ground here, on the dry land, he can actually put in some stakes into the ground. He can measure their distance as 25 meters, and he can even use an instrument that will measure the angle measurement here to point C and measure the angle that's from here to point C as well. So these are all things that he can figure out because he's over there on dry land. He's available to do it. But to actually get the distances, he has one choice, which is to go out into the water, whether that means take a little boat or swim out there, or he can use trigonometry, which is what we're going to do. All right, so specifically this question is just going to ask for what's the distance to B. So we're not going to be actually solving for A, though you could do it. All right, being that this is part of the law of sines notes here, we're going to go ahead and assume that that's what we're using. So I set up a template, which is for a proportion. I got my 2 fraction bars and I got my equal sign. Now, the most important thing that we do for trying to use the law of sines is identify a pair of angles and sides, or a pair of an angle and a side. 2 that would be across from each other. So when we take a look at the picture, the 110 degrees is across from A, one of those distances that we can't figure out right now. We don't know those at the beginning. Okay, and then the 20 degrees is also across from the B. So the 2 angle measurements that have been provided here are not matching up to sides across from it, which means I can't complete one of the sides of my proportion. But the 3rd angle, which is not known here at the moment, is across from the 25 meters. The only side length that we have is across from that blank angle. But that blank angle, you can actually figure out what it is because all 3 of these angles need to add up to 180 degrees, the triangle sum theorem. Okay, so if we take these 2 together, you get 130, subtract the 130 from 180, and that means that this angle has to be 50. Okay, so the engineer is able to measure these 2 angles on his own. That one has to be 50 degrees. So now that we have that one, we can create a pair, which means that we can complete one side of the proportion. Okay, so we got the sine of 50 over 25. And what we're interested in figuring out here is side B. So I'm going to look at the angle that's across from B, which is 20 degrees. So that's going to give us the sine of 20 is over B. All right, now our proportion's all good because we only have one variable in there. We only have B, and we'll go ahead and solve for that. The first step of this, so we're using cross products again. You're always going to use those. You're going to take the product of the diagonal. All right, so to type that in, I go with the regular number, the 25, and then I just follow up with sine 20. That is going to give us 8.55. Again, it doesn't represent anything in the picture. This is just the product of that diagonal. But when I divide it by the sine of 50, not just 50, but divided by the sine of 50, I'm going to get B. So I divide by sine 50, and that comes back as 11.16. So that is the final answer. In this case, that would be meters, right? In this case, you don't have that extra step of doing an arc sine. So when you're solving for an angle, you have to do an arc sine at the end. If you are solving for a side length, it's just a real quick cross product. Just multiply, divide by the sine of whatever angle you know, and then you've got your side length, and that's it. All right, now if we were interested in figuring out A, you basically just repeat the whole problem, but swap out 110 degrees for the 20, because you want to keep that complete ratio here, that complete fraction. You want to use that one, and then for the other one, you can just add in the information that would apply to figuring out that one. We have one more thing to address here, which is called the ambiguous case. Okay, so the ambiguous case happens when we're attempting to use the law of sines to solve for an angle measurement. If you're solving for a side length, it has nothing to do with this, and that's fine. Okay, but if you're solving for an angle measurement, it's possible that when you do an arc sine at the very end of the problem, you're going to get one of two correct answers. You can actually have two correct answers when you're solving for an angle with the law of sines. But it only occurs in certain situations, and there's a really easy way to determine whether or not you actually have that happening. And it's also really easy to figure out what the other answer would be. So it's just this little final check that you have to do. Okay, so if you're solving for an angle, the supplement of the angle may also be a solution. So suppose we already do the law of sines and we come back with an answer that's like, I don't know, 70 degrees. The answer is 70 degrees. Then 110, which is a supplement, might also be an answer. Okay, so we're just going to verify that the supplement along with the given angle doesn't already exceed the triangle sum theorem. Okay, so what that means is that you've already got one angle to start with. Then you're going to solve for another angle. Okay, and that'll be an answer. That's going to be a given answer. The supplement to that answer, as long as that supplement plus the angle that you've already got does not exceed 180 degrees, then you can accept that as a second answer. If it does exceed 180 degrees, then it is not going to be a solution. Okay, so let's take a look real quick at example number 1. Okay, so in example number 1, we solved for an angle measurement. We got 28.2 degrees. All right, there is a chance that the supplement to that angle is also an answer, and we could just redraw the picture in a different way, okay, and let the supplement to that be the answer. But the supplement to that, I don't know if I can do it off the top of my head there, so I'll just take 180, subtract 28.2. The supplement is 151.8. Okay, now that actually can't be another answer in this problem, because if we use 151 degrees for our unknown angle, and we've already got 126 degrees for angle S, then we've exceeded our 180 by a lot. So this will be the only answer. Yeah, so one of the things that you're also looking for at, maybe not at the very beginning of the problem, but when we start considering the possibility of a second answer, is just to check and see if this is an obtuse angle, then the supplement to the answer that you get is not going to fit within our 180. So it's more, if you start with an acute angle, when you get your answer, check the supplement to that one and see if it would still work out. Whenever you're going to be doing the law of sines as a problem, you do have to have 3 pieces of information. This diagram that we're going to use to animate the ambiguous case only identifies 2 of the things. So I'm going to show you where the third one is. Okay, but the 2 that we already have, this angle right here is 30 degrees. So that's going to be locked into place, which means that the direction of that line and the direction of this line are set. Those won't be changing. All right, now this segment does have a set length, which is going to be 10 units. Okay, so it's definitely going to stop at that point. So this piece does not move at all from the diagram. The bottom base does not have a set length. That's just going to depend on when the last side closes in. So we don't know that one. Okay, so those are the 2 pieces we know, the angle and the side. The other piece that we would know here is the side that's across from angle A. So we know that this has a set length, but we don't know the angle that it makes with the other side. Okay, so you can imagine you have like a hinge here, and this is swinging back and forth. Now, and that's what the arrow kind of describes here. It describes the movement that C could follow, which would be circular, right? It would spin around there. All right, now if we were just to let go of C and let it drop, it's going to swing into this spot and make contact there. And that is going to complete your triangle. Okay, so if you're doing a law of sines problem, you'd have this angle, you would have that side, you'd have that side, and when you do all of your math from law of sines and you take that arc sine at the end, you're going to get this angle measurement right here, which you're going to notice in this diagram is an acute angle. It's there. But there's a second answer, which is the supplement to that one. Okay, so I'm going to take a compass, and I'm going to attempt to match it up with that arc. That's going to be a little bit hard. And I'm going to show you that if we don't allow it just to stop at that one spot, but continue to swing through, it makes contact at a second spot, which is over here. Now I'm going to go ahead and connect that one. Okay, so if I connect here, this angle would actually be the supplement to the one that we have here. Okay, you can see that's an acute angle and this is an obtuse, and they are supplements to each other. We could verify that because we have an isosceles triangle right here, so this angle would be the same as that one. This and that make 180, so this would be the supplement. So that's old geometry stuff there. But this angle would be the supplement to that one. But how does that still work out? Well, we still got the 30 degrees. We never changed that. We still have the line segment of a 10, okay? And the side that we were given across from the 30 is still the same size. It's just a matter of whether or not it makes contact further out here or closer in at that spot. Okay, so a little bit of a recap here. If you're doing a law of sines problem and you're trying to solve for an angle, you're attempting to solve for an angle, and the given angle is an acute angle, when you do your math, you're going to get an answer that's an acute angle for your other one, the one that you solve for. Okay, you need to check, you need to consider that the supplement to that angle is also going to be an answer. Just make sure that when you do take the supplement to it and you add it to the given angle, that you have not exceeded the 180 rule. And if you haven't, then you've got two answers.
Later, blah.